I think we're about good to get started. Thank everyone for joining us. We're excited for this Microsoft workshop today. If you have any questions, feel free to drop them in the chat. We'll do our best to monitor them as we go. This will be recorded and posted to our YouTube channel later. So now I'll hand it off to Maria to get this workshop started. Thanks for being here, Maria.
Thank you for the introduction. Hello, everybody. My name is Maria Mikhailova. I'm a principal quantum software engineer here at Microsoft Quantum. And today I'm going to introduce to you a Microsoft challenge for QRISE and talk a little about the big picture, the context of why we're offering you this challenge, and then show you some of the tools that you're going to be using if you choose to pursue this challenge. Before we dive into the challenge details or the tools, let's take a minute to take a look at the state of the quantum computing industry and how this challenge fits into it. The ultimate goal of quantum computing, of all the research that we're doing on building quantum computers, is, of course, to be able to solve problems that classical computers cannot solve, at least in reasonable time. If a classical computer can solve something in a lifetime of universe, we do not count this as it being able to solve this problem. And the big question, of course, is at what point quantum computers are going to be able to solve practical problems. If you followed quantum computing progress at all, you probably know that the milestone of so-called quantum supremacy, being able to solve an artificial problem that a classical computer cannot solve efficiently, has already been achieved. And now the next question is, of course, being able to solve a practical problem, a problem that somebody is willing to pay for, that classical computer cannot. And the question is, how can we do this? For the past quite a few years, a lot of work went into trying to figure out whether it is possible to achieve quantum advantage using NISQ devices, noisy intermediate scale quantum computers. In the past year, maybe even in the past half a year, the shift seems to happen at which the community moves from trying to explore algorithms that run on NISQ machines to admitting that probably algorithms running on noisy machines are not going to give us practical advantage, and we do actually need fault-tolerant quantum computers to run much larger algorithms than the ones you can do on small devices, small noisy devices. And this means that we need to regroup and figure out the resource requirements for those big quantum computers running error correction and running long-running algorithms, to figure out how to build computers of sufficient size and sufficient performance. And this is where resource estimation comes in. What does resource estimation do? It allows us to put numbers to algorithms. When we discuss a quantum algorithm, when you first learn, for example, Grover's search algorithm, you're going to learn something along the lines of the brute force classical algorithm is going to take big O of n queries to solve this problem, where n is the size of the search space. And Grover's search is going to take big O of square root of n queries, which means it gives us theoretical speed up. Well, now knowing this is not enough for us. We want to know how much actual time it will take to run Grover's search for a problem that we could potentially solve using it. And we want to know how many qubits it would take for a computer to be able to run Grover search of this size. And we want to be able to compare this runtime with the runtime of classical algorithms on classical hardware. And not just a brute force algorithm, because nobody solves most of the problems, search problems, using brute force algorithm. We want to compare it with the best-in-class classical algorithms. Quantum resource estimation allows us to make this kind of estimates for quantum algorithms. And the best thing of all, it allows us to make this kind of estimates in advance. We don't need to actually have a 1,000,000-qubit quantum computer to figure out how long it will take it to run this specific algorithm for this specific problem instance. We just need to implement the algorithm and then provide some parameters of the computer we expect it will have. And then we get the time estimate. And this way we can learn quite a bit about a lot of aspects of our work, both about the software and the hardware. That allows us to shape our work, that allows us to figure out our priorities in our work. Resource estimates allow us to do this in multiple directions. First, resource estimates are done under certain assumptions about the hardware that we're building. When we do resource estimates, we provide information such as the time it takes to apply a gate on a computer, the noise level of individual gates, the noise level of individual qubits, the error correction that the computer is running to convert physical qubits into logical and perform computations on logical qubits with less noise. And all these assumptions are converted into our estimates, the time it takes to run the algorithm and the number of qubits it takes. And this way, we can figure out whether these assumptions are sufficient to run our algorithms, whether having gates with microseconds operation time is enough, or whether we actually need to push our hardware to perform gates in nanoseconds instead. Spoiler alert, we do need to push them. So this allows us inform to our hardware design. This is the first reason why we want to do resource estimates. The second reason is we want to be able to estimate whether certain quantum algorithms are efficient. Is it enough to have a quadratic speedup like Grover search is offering over the brute force search to say that this algorithm we expect will give us practical advantage? Or is it not enough? Do we need better speedups? Spoiler alert, we do need better speedups. Right now, we believe, based on the research we did, based on resource estimates that we did, we believe that Grover search and the kind of speedups offered by it, quadratic speedups, are not going to be sufficient to give us quantum advantage. As the overhead of implementing computations on a quantum device that is slower than classical ones, plus the overhead of implementing things as a quantum computation as opposed to classical, these things taken together make quadratic speedup not sufficient to give us advantage. And third, of course, we can compare different implementations of the same quantum algorithm to figure out which one is more efficient. And we can define efficiency in multiple ways. We can choose the faster algorithm, the algorithm that takes less space, less memory, or some kind of combination of these factors. And again, we can do this a long time before we have quantum computers that allow us to actually run these algorithms. So hopefully I have convinced you that resource estimation is an interesting area to work in. I spent quite a bit of time over the past year working on resource estimates for different algorithms, and I'm planning to keep working on that. So that's why I'm offering this challenge to you. So to make things a little formal. In this challenge, we are inviting you to pick a quantum algorithm, implement it, get the resource estimates for it, and do some kind of analysis with them. The papers that are linked in the GitHub repository offer you some examples of the work that can be done this way. For example, you can compare different implementations of the same algorithm. One of the example papers compares 3 implementations of multiplication algorithm. And this kind of thing is actually interesting. When you think about algorithm involving multiplication, you don't think of multiplication as something complicated, right? I mean, it's multiplication. How hard can it be? Turns out when you do it on a quantum computer, it is hard. And it takes time and it takes qubits. And this kind of insights that you get, they make you think about what does actually go into building quantum computers. There are some parts of it that I never actually thought deeply about until I started doing resource estimates and looking into them, into why they look like this. And so I hope at the very least you will learn a lot about the architecture of fault-tolerant quantum computers, and of course about the quantum algorithms that you choose. And that's probably quite enough of an introduction. And now let's see some code. And as we see some code, I will tell you a little more about how resource estimation works and the assumptions it makes. And then, of course, you will learn a lot more as you read the documentation and as you read the papers. So the main environment for working with Azure Quantum Resource Estimator is Azure Quantum Development Kit. I shared the link to set it up in the Slack because I realized that in all the resources for the challenge, I didn't include the actual installation instructions. The environment I highly recommend you to use is Visual Studio Code. It is easy to install and convenient to work with multiple languages, and the extension Azure Quantum Development Kit offers you very nice C# support. And you probably want to install a Python package for C#. It is possible to get resource estimates with just the C# code without involving any Python in the process. But it is a bit trickier to work with them, to extract specific numbers from them and, for example, build your own plot based on them. I will show you what I mean in a moment. So to start with, let's take a look at a very simple example. Okay, I'm not going to need this, right? A very simple example, resource estimation of a random circuit. This algorithm doesn't do anything interesting. This circuit was used in experiment on simulating quantum algorithms. The experiments that looked at how good certain simulation approaches are at simulating quantum circuits. So the circuit itself is very simple. And here is the C# code that implements this circuit. You can see that it takes 2 parameters, the number of qubits and the number of gates. It allocates that many qubits, and for that many gates, it chooses each next gate randomly. It's either a controlled Z gate or a Hadamard or a rotation. And if it is a controlled Z, it's a gate between 2 random qubits. And if it is Hadamard, it's applied to a random qubit. And if it is rotation, it's applied to a random qubit at a random angle. Absolutely nothing exciting is going on here. And this code, here I'm using it in a Jupyter notebook. So I can define the C# code inside a Jupyter notebook cell if I'm using %% C# magic. Oh, and I should mention this, all the examples I will be showing today are part of the official Microsoft /Q# GitHub repository. There is a link in the challenge description. So I didn't do any custom sample development for the demo. You will be able to find all the files there and repeat everything I did here. So we have defined a random circuit, and then we run the resource estimator on it. Here I'm running resource estimator from Python. So I'm specifying the number of gates and the number of qubits, and I'm specifying the random seed that is going to be used for generating this circuit to make sure that every time you run this notebook, you get the same circuit. And then I call qsharp.estimate. This is how we call the resource estimator. If you want to run the same code on a simulator, you would use qsharp.run or qsharp.eval. But then the thing is, you cannot really simulate this circuit or the circuits that are going to be even more interesting for resource estimation, because it's interesting to run resource estimation not on 1, 2, 10, 20 qubit circuits. It's interesting to run it on circuits that take thousands of logical qubits. But first, let's see the resource estimates for this small circuit. And this here are the resource estimates. Now, when you run resource estimator, you get a lot of data back. And quite a bit of work is going to go into figuring out which fields describe which parts. One of the papers in the list of resources goes in detail through the process that resource estimator takes to convert the program you give it to resource estimates and the parameters that it produces in the process. I'm going to give you just a little overview as we go so that you can follow what we're doing here. But then again, more digging is going to be required to deeply understand what's going on here and all of the numbers. So the top 3 parameters that resource estimate produces is the runtime. The time is going to take the algorithm to complete on a quantum computer under certain estimates. The physical qubits, the number of physical qubits that is required, and a parameter called RCOPS. It's decoded as reliable quantum operations per second, similar to the classical value. I believe it's flops, floating point operations per second. That's a metric that can be used to define performance of a quantum computer irrespective of a specific algorithm, same as how flops can be used to describe performance of a classical computer irrespective of an algorithm. And you can see that for this circuit, the runtime is 4 milliseconds. That's perfectly acceptable. The number of physical qubits is over 1 million. And this is the part where personally I was shocked the first time I saw this kind of resource estimates. It turns out that there are multiple pieces contributing to this quite astonishing number of physical qubits. I mean, you have 43 logical qubits and they're encoded into 1 million of physical ones. Not quite. So multiple things happen as we convert our program into our resource estimates. First of all, you can see a bit of a decoding right here. And this decoding breaks the total estimate into 2 parts. there is a number of physical qubits that are used to implement the algorithm logic itself, the computation itself. And then there is a very different number of qubits that are used to execute the T-factories. Now, the assumptions under which resource estimator works start with the fact that there are some gates that you can do using multi-qubit measurements. And there are some gates that you can track classically. And there are some gates that you have to generate using state distillation. You will see that Clifford gates, poly XYZ, C nodes, resource estimation is going to just ignore. It assumes that they are tracked classically. I think it's called poly frame tracking or Clifford frame tracking. It is a little early in the morning to recall the specific term. But they are tracked classically and they affect the way you do measurements in the end of the algorithm. So you don't apply them to your computation and it doesn't take quantum resources to apply them. Now, some gates are converted into multi-qubit measurements. And some gates, such as T gates and arbitrary rotations, cannot be done using either of these ways. To implement an arbitrary rotation, you break it down into a sequence of Clifford plus T gates. And those T gates you have to get from somewhere. And those T gates are generated using separate processes called T factories. Where? And you can see that most of the qubits, like over 1 million qubits, are spent on executing T factories. Effectively, the number of physical qubits that are used to implement the algorithm logic is something like 2% of the total number of physical qubits. So barely noticeable. It turns out that here, this random circuit uses quite a lot of rotation gates. Rotation gates require a lot of T gates to synthesize them. And the gates that are being synthesized, the T gates, take a lot of qubits to run those factories. And I will show you how to make some choices to reduce the number of physical qubits at the cost of making the runtime a little longer in just a moment in the next notebook. Let me answer a question that came into Q&A. So the question is where to find this notebook. And the answer is all the notebooks here in the demo come from this folder, Q-sharp samples estimation on GitHub, and this particular notebook is estimation random circuit. Okay, so those are the main estimates we get. Now let's see what are the other kinds of data we get out of this execution. You can see that the parameters and the data generated during resource estimation is broken down into several groups. These groups roughly correspond to the steps that resource estimation does. And let's see what they are. So the first step corresponds to pre-layout logical resources. The first step resource estimation does, it goes through the program. It doesn't simulate it, of course, because you cannot simulate, generally speaking, programs that are big enough. And it counts the gates that are interesting to it and the qubits used in the algorithm. So you can see that the number of logical qubits is 43. exactly as many as we allocated in the program. We have some rotation gates. And we have the rotation depths. Rotation depths is basically, we try to parallelize gates happening, well, in parallel. And here they're not all happening in parallel because there are some control Z gates between other gates. So this is the step in which the program is analyzed on the logical level. After this, we do some conversion steps. Then we go to resource estimates breakdown. We convert the logical number of qubits to logical algorithmic qubits. This step is basically laying out the logical qubits that we're going to use in our computations in a sort of a grid in which stripes of logical qubits are separated by stripes of connecting qubits that are going to enable our all-to-all connectivity between all logical qubits. This roughly doubles the number of qubits plus some extras to account for the tail ends of the rows. For the depths, we convert our rotation depths into logical depths, which is converting our gates into multi-qubit poly measurements. Now I'm not going to try and hand wave my way through explaining to you how this comes about. I recommend you read a paper in which I wrote it down carefully. But basically the idea is that you use measurements to apply double controlled gates. The two main kinds of gates the algorithm cares about are rotations and multi-controlled gates. And rotations you synthesize using Clifford plus T's, and multi-controlled gates you synthesize using Toffolies and some extra T gates. So the algorithmic depth converts those gates the algorithm cares about into depths in terms of multi-qubit measurements. And this gives us the next level under the logical representation, the representation that is going to be closer to how the algorithm is actually going to be executed. So we break this into quantum intermediate representation. And this tells us about how our program is going to be executed. This was the top-down part of the algorithm. Now the bottom-up part of the algorithm takes into account the parameters of the physical device that we are assuming and of error corrections that we are assuming, and brings this data to connect it with our program representation and to get the actual resource estimates. Let's see. As the section of physical qubit parameters, those are inputs to the algorithm. You can specify and use one of the predefined instruction sets, architectures, or you can come up with your own. By default, the parameters are gate-based technology with certain times that are spent on measurements on single and multi-qubit gates, the error rates. And again, the documentation lists specific parameters for all of these values. And then another parameter you're using is the error budget, the level of error with which you are fine in your algorithm. This can be algorithm specific. And then there are logical qubit parameters, the error correction scheme you're going to use, and the parameters of this scheme itself. Now, in this group, some of the values are given as inputs or assumed as default. Some values are calculated during resource estimation. For example, code distance and the number of physical qubits are calculated during the process of resource estimates, because the code distance basically depends on the noise level in the system on the device and on how long your computation needs to be. The longer your computation needs to be, the lower you need to make the noise of your logical qubits, and the bigger is the code distance that you need to use. And that covers error correction. Oh, and the T-factory parameters. T-factory parameters are also a combination of inputs and ones computed during the execution. The number of T-factories and their parameters are calculated based on the number of T-gates required for executing the algorithm. And on how fast you want this algorithm to run. So you can see that T-factories are a major contributor to the number of qubits in the execution. And this is all on a very high level that goes into resource estimates. Now, this clickable interface is very nice, but it's pretty inconvenient to actually get numbers out of it, especially if you want to run 100 resource estimates for different inputs and build some plot based on them. So what we're going to do, why I did this is in a Jupyter notebook actually, because this result is not just a nice interface, it also is presented to you as a JSON file, as a dictionary of dictionaries. So you can access the specific values you're looking for, like this, like you access any values in a dictionary. So here I extracted some specific numbers I was looking for. And basically this is how you would do it if you want to extract resource estimates programmatically in Python. And I think I have an example later that shows you how to do this as well. If you just save the resource estimates into a file, you're going to get something like this, a JSON file with a lot of fields. And again, there is documentation that tells you which fields are input parameters and how to specify them, and which fields are calculated and how to access them. This is it for the main workflow of resource estimation. Now we have some time. Let me show you some other interesting things. One thing that is interesting is the trade-offs in space-time. By default, resource estimation optimizes for time. It looks for the shortest execution time, and it tweaks the parameters that it can tweak to ensure that the execution time is as fast as possible. In particular, this means that for the T-factories, it's going to spawn as many of them as are needed. And basically, each one of them is going to produce a T-state. Not quite that simple, but very often this is what happens. But we can actually play with this a little bit. And a notebook estimation frontier widgets from the same folder shows you what this looks like. It takes a more complicated example, dynamics simulation, and uses the tools that resource estimation provides to explore these space-time trade-offs. You can see here how we can provide specific qubit parameters to run multiple estimates of the same code at once. Here, for example, we are running estimates for different default hardware platforms with different gate times and error levels. And for some of them, we are also using different quantum error correction scheme. And here, all of the estimated types are frontier. Well, this means that we're going to build a Pareto frontier of those space-time trade-offs. You can see that the result of this estimation, if we plot it very carefully, looks something like this. We have a list of the platforms for which we did the estimate, and we have the best runtime here. But those best runtimes are associated with, frankly, incredible numbers of physical qubits. I mean, we have 7 million qubits. We need to try and bring this down a little. And the space-time diagrams shows for each platform, each line corresponds to a single platform, the different values of time and number of qubits that we can get. How do we get it? The fastest way to run an algorithm is to build as many T factories as are necessary for the T gates and produce the T gates as fast as possible. But what if we slow down our algorithm execution a little bit? If we don't need to produce the T gates as fast as possible, we can actually have each T factory produce multiple T states. It will take longer time, but we're fine with that because this means that we will need fewer T factories. So this will slow down our execution, but it will slow it not that much at the cost of significantly reducing the number of qubits. For example, here, if we look at this orange line, the fastest execution is, well, milliseconds. But that execution corresponds to 500,000 qubits. That's a lot. If we play with the number of T factories, if we slow down the execution, we go from milliseconds to seconds. So we get 21 seconds execution time. Frankly, I'm not going to personally notice the difference in execution time between milliseconds and 20 seconds. It's not the kind of execution time that will make me go and make myself tea while I'm waiting. But the number of physical qubits goes from 500,000 to 30,000. And this kind of order of magnitude reduction in the number of physical qubits is actually pretty nice. Another effect you might notice here, some of those lines have those jumps that correspond to not so smooth trade-offs. Those jumps are actually when error correction parameters change. If we look at the blue line, we start with code distance 9. And we have runtime of 200 milliseconds and 600,000 physical qubits. As we try to make the runtime longer and the number of physical qubits smaller, the things are pretty smooth. The code distance remains 9. But then here, the code distance is increased. It jumps to 11. Here, since our algorithm is running slower, it has more time to have the noise affected, which means we need to put more effort into error correcting it, into fixing this noise. And this means that at some point, code distance has to increase. So this is why here the execution time is increased without a very significant reduction in the number of physical qubits. But then at the code distance 11, we can slow the algorithm down and get again to pretty much an order of magnitude reduction in the number of physical qubits. And you can see the detailed breakdown if you click on a specific point. You can see, for example, the space diagram, the breakdown between physical qubits and qubits required for T factories. And now you can see that here, the T factory qubits is actually smaller than the number of logical qubits required to run this, because we are using one T factory and letting it generate all the T states. So we're not going to be able to slow down execution further to reduce the number of qubits, because we are already down to one T factory and we have to have one T factory. To compare the breakdown, if we go to the top point on this line, you can see that the algorithm qubits are still 30,000, but the number of T factories is 500,000. And in this setup, there are 200 T factory copies, so they overwhelm the number of qubits quite a lot. Okay, this was it for the space-time trade-off. And I think I had another example to show you, two examples. So this example is Shore, again from the same folder. But this example is standalone Q#. You can, in principle, run resource estimates from a Visual Studio Code directly without having a Python interface. How can you do this? You put your code in a Q# file, and then you go to the command palette, Ctrl-Shift-P, amazing. And once you add a Q# extension to Visual Studio Code, there are a bunch of commands that allow you to do things with Q#. The command Q# calculate resource estimates is the one you're looking for. So here you can choose the platforms you want to use. For example, all of them, except Mayoranus with Surface Code. Mayoranus work better with Plaquette code. And you enter the error budget, which is the default one. Oh, actually, for Shore's algorithm, you want to make your error budget 1/3. It's a quirk of an algorithm. And a friendly job name. And you can see that you can get the same visuals here. They look differently because it's a different algorithm being evaluated. But you can get them in Visual Studio Code directly. And you can get details on a specific point. The reason I prefer to use it from Python because it's much easier to access resource estimates in Python programmatically. Because if you're going to be doing research, publishing papers, you don't want to put the default space-time diagram as the visual in your paper. You want to have your plots custom made. And the last example is a pretty big one. It's the double factorized chemistry application. And this is an example of an algorithm that includes pre-processing, and quite significant pre-processing before the quantum component. You can see that here, so in the Jupyter notebook I showed you before, it basically called Q# code and printed the results. It didn't do any pre-processing. In chemistry, there is quite a bit of pre-processing, as you're going to see if you explore it. Starting from reading the molecular properties from FCI-DOM file, converting it into inputs to quantum code. Basically, all this Python is doing some math. And then you form the Q# string that you want to evaluate, which basically calls Q# entry point, double factorized chemistry operation, with these parameters that it took this whole time to calculate. And then you get resource estimates for this string with those parameters. And here it also shows you how you can provide parameters in a program to specify which platform you want to use and which quantum error correction scheme you want to use. And then it writes the results into JSON file. So this is a more complicated example that I'm showing to you, mostly as an example of Python is not just for plotting your data. Python can also be used for pre-processing. Or if you are exploring a hybrid algorithm, it can be used as part of the hybrid algorithm. And this is the last sample I had for you. Now let's see. Oh, right, I should probably say something about the challenge itself. So in a challenge, we encourage you to do something similar to what I have shown to you right now, but more nicely organized. I will be occasionally taking a look at the Slack channel, so you can ask your questions there. And I have a wonderful volunteer, Brian Goldsmith, who generously volunteered to keep an eye on the questions as well. If you have questions about Azure Quantum Resource Estimation or Q#, do post your questions there. And if you have questions now, we have time to answer them.
Maria, it's Brian. I just wanted to say there was one question regarding using like Penny Lane or other frameworks. And I just wanted to point out that the resource estimator works directly with like Qiskit or Q# or anything else that can be kind of put into a QIR format. And so for something like Penny Lane, there are ways to do that. I mean, even using OpenChasm, if you can translate a circuit into OpenChasm and then something with Qiskit, you could take that and turn that into a Qiskit circuit, and then use the resource estimator with that.
All right. Thank you. That reminds me. You can, as Brian just said, use Qiskit with resource estimation. But right now, I showed you the kind of modern resource estimator integrated with Visual Studio Code. Qiskit resource estimator is available through Azure Quantum as a service. If you check out the documentation, and if you give me a second, I might even be able to find it. It walks you through resource estimation for Qiskit, but it requires using Azure Portal. I know I looked at this page this morning. And to use Azure Portal, you need, well, you need an Azure account. You need to create a workspace, which is a bit of pain. I'm actually very happy that we have the modern QDK that allows you to run things locally. Apparently this documentation page disappeared over the past hour. Here it is. Yeah. there is a link, different ways to run the resource estimator, and Qiskit. For Qiskit, you need to use the Azure portal. And while I was looking for the documentation, any questions?
Thank you, Maria, for that workshop. And I will end the recording here in a moment. If anyone wants to ask a last minute question without the recording going, feel free to unmute and ask Maria final questions. Otherwise, I'll upload this workshop video to the YouTube page of the Quantum Coalition later today or tomorrow. So you can re-access this video, or anyone who missed it will be able to watch as well.